Okay, we're live. So, a relation is a rule that associates the elements of one set with the elements of another set. So let's give you some relations and see if you can see what the rules for them are. Okay, so I'll try to do this with, I'll do this up and down. So here's here's elements of set X and elements of set Y. Well, set X is going to go 1, 2, 3, 4, 5. And set Y is going to go 1, 4, 9, 16, 25. And you could put little arrows from here to here if you want to, but I'm kind of happy just not bothering with that. We'll just kind of understand that if we list a set and another set in a T-chart pattern, then what we're saying is that 1, apply a rule, becomes 1. 2, apply a rule, becomes 4. 3, apply a rule, becomes 9. This one was pretty easy. What's the rule for this one?
Square.
So basically, the rule is square X to get Y. Yep.
Okay, I thought so.
How about you square root y to get x?
That's a good point. You could go the other way. You could say you could square root Y to get X. All right? Keep in mind that, yes, some of those rules are reversible that way. Here's a different one. This one might be a little tougher. Or maybe not. I don't know. Depends on your background. Oh, I don't need that much space. Let's start that over. There we go. Okay, how about, we'll keep this one simple again. 1, 2, 3, 4, 5. And on this side, we're going to go 1, 4, 7, 10, 13.
Oh,
What do you think it is?
plus 3 or double plus. I had it.
What do you think it is?
Oh.
Okay, that's a good, you've got it in a sense, right? As X increases by 1, Y increases by 3.
X plus 3.
But
Nope.
it's not quite X plus 3.
It's 1.
X minus 2 plus 3?
It's the previous of y.
No, because 5 minus 2 plus 3 wouldn't give you 13.
The previous y.
There it is. So you're very close. What do you think it is again? 5 times 2 plus 3 works. 4 times 2 plus 3 does not make 10.
It's the previous y plus 3.
See, here's the problem with the previous number plus something, is that I kind of like to be able to jump anywhere I want in the pattern. What do you think it is? There it is. The rule is take X times by 3, then add 2 to get Y. Oh, yeah. Thank you. Minus. And notice both of these relations that we have here, example 1 and example 2, if you want to call them examples, both of these relations you could very easily express algebraically. You could call this y equals x and then put a exponent for squared. And this one you could say that y is equal to 3x minus 2. And you should have learned actually in grade 7 and 8 that you could have got this pattern by saying, okay, what you noticed right away, this is going up by 3 when this is going up by 1. So your x number is being times by 3 over 1, also known as the slope of it if you graphed it as a line. And then trail the pattern back to when x is 0 to figure out what the y number is, and then that number has to go here. So if you counted backwards from 1, counted backwards by that 3, you get minus 2. And of course, saying 3 divided by 1 is kind of silly. So you'll just say,
Simplified to
you just
three
simplify it to that, yeah.
Ah.
3/1.
I have to give my brain a refresher, I'm an idiot.
It's all good. So that is, of course, how you would graph something like that, too. The -2 tells you this number right here is -2. And this 3/1, again, I know I look at it as a 3, but I think of it as a 3/1. In grade 9, you were taught, well, that just tells us that to get from one point to the next point, you go up 3/1. Remember doing that? And then that would be your line. Desmos's graphing calculator, of course, can help you do stuff like that, but you should be able to graph straight lines coming out of grade 9. And we, of course, call straight lines linear. Remember, you called that linear algebra. And if you can't graph straight lines by just, well, I guess the other thing I could have done is plot all these points and then join them with a line. But if you give me an equation, I should be able to get a line too. So that's something that we'll have to make sure we review going forward. All right, let's give you a couple more of these. If you don't have enough room here, just, you could write them on loose leaf. I'm going to get rid of all this. All right, so next example. Suppose x and y, what's the rule for this? Suppose I go 1, 1, 2, 3, 4, 5, and I'll go 0, 1, 0, 1, one more, 0. What's the rule here? There you go. That's my rule. Even numbers, oops, I missed the N on numbers. Umbers? Even numbers make y are 0, and odd numbers are 1s. Now, I'd have a hard time imagining an equation that would make that work. But certainly it is a relation. It is a rule that helps me turn the x numbers and the y numbers, and it would work anywhere, right? I could jump to the number 4,712. 0. There you go. All right. Here's another one, just to show you that, again, they don't always have to be related to equations.
The previous one would be really easy in computer science.
I suppose. All right, so suppose we had, okay, let's do this. Let's make it a little bigger one. Suppose we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, let's just do the first 10. So it's going to be 1, 1, 1, 1, 1, 1, 2. 1, 1, 1.
Bring it up to 20.
I think this would be, hang on, 3, 1. Okay, my chart's got to keep going. So 13's back to 2.
What? Nope. 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 Doesn't work.
Okay, let's jump a little. What do you think it is?
Syllables.
You exactly got it. I was going to give you 127 and tell you that that's 7. And then I was going to give you 5,483, which is 9. And then I was going to ask you to guess from there. But he got it already. So what's my rule? Number of syllables. Syllables? EL?
Call it UL. And we'll
Syllable? That better? Number of syllables in word of X equals Y. Good luck getting an equation for that. So you get the idea. The rules that turn X's into Y's can be just about any kind of rule you want. In fact, a lot of what we're going to do in this particular chapter isn't even going to be numerical. We just want you to understand the idea, the concept behind there's a relationship between this set of things and this set of things. And we'll worry more about those things actually being numbers later on. as you'll see here, the next couple of examples aren't even numerical at all.
Oh, no, that-
For example, we can associate fruits with their colors.
Yay.
So let's represent this relation in words. In words, we would say apples are red or green, because apple has two different elements in the fruit set.
It's the color of the fruit.
Blueberries are blue.
Who knew?
Oh, I guess I should say blueberries. I should say, hang on. I don't want to write a whole new sentence. Blueberries and huckleberries.
Huckleberry thing. They're more black.
Oh, hang on.
They're like purple.
Huckleberries are blue. And lastly, we could say then that also from this list we have learned that cherries are red.
No, they're hot rod red.
So, express this relation now using something called an arrow diagram. Now, arrow diagrams, you're probably going, what's the difference between an arrow diagram and just writing a chart? The arrow diagram can be much shorter than the chart. Especially, you never have to write, say, apple twice, because in this case, you can just write it once, and then draw an arrow to red, and draw an arrow to green.
You can look at the other.
And there you go. And then, of course, you've got blueberries, and you've got cherry, and you've got huckleberry. I hope I'm spelling huckleberry right. And blueberry is, of course, blue, but so is a huckleberry. And, of course, cherries are red. And we call that an arrow diagram. And believe it or not, even in fairly high levels of math, they use these diagrams a lot when they're showing fairly complicated relationships between things that might not even be easy to show in an algebraic or a formula way what the relationship is. So to get you used to using them, we'll stick to things like words, but you know, I could make you an arrow diagram with numbers. Like again, we could do how about we do 1, 2, 3, 4, 5, 6, and then we do something like this. Prime and the word for not prime is composite. So which way does 1 go? Neither. Very good. 1 is not a prime or a composite number. I thought I was going to fool you with that. Nice job. 2 is definitely prime. 3 is definitely prime. 4 is definitely composite because again it has a factor that is not prime. Or sorry, that's not true. It has more than one factor that is prime. 5 is prime, and 6 because it's got a 2 and a 3 is composite. So you can get back to numbers with these kinds of diagrams too, but for the most part, we're going to use words for this part of the unit.
We still technically use words.
That's true. I did sort of use words, but I could have come up with a symbol for prime. Oh, that's true. Why did I make a new red? Good point. Thank you. The whole thing I was telling you is that these arrow diagrams save time, and then I just wasted it. Cherries are red. Thank you.
Let's overcomplicate things. It's fun.
That was a very inefficient arrow diagram I had. Thank you for helping me fix it. Okay, so now, a set of ordered pairs. What do they mean by ordered pairs? Ordered pairs means X element, comma, Y element. And that's assuming I call the sets X and Y. In this case, I'm going to call them fruit and color. So on the left, it's apple, apple, comma, red, apple, comma, green.
So it's the opposite of the oval diagram.
So
It's
they're
just
variables.
complication.
They are variables essentially. They are essentially like, you know, an X, comma, Y. The same way you'd put coordinate pairs down if you were graphing something. Cherry, comma, red. And finally, the one that I have a hard time spelling here, huckleberry blue, which is, I guess, why the dog Huckleberry Hound was blue. Is that a cultural thing that you'd even know, Huckleberry Hound? He used to be on the same cartoon show as Yogi Bear.
Oh. I haven't watched the old Yogi Bears in years.
I have a DVD of them all. They're quite good.
I have the Yogi Bears Christmas DVD.
Ooh, Yogi Bear's Christmas. Cool. All right, let's take a look at one that's slightly more numerical, and it starts with a bar graph. Consider the relation given by this bar graph. Different towns in Manitoba can be associated with the average time in hours that it takes to drive to Winnipeg. So represent this relation as a table of values. Okay, so as a table of values, you'd just rewrite this numerically. You'd go town and I guess hours. I guess you could write this in full, hours to drive to Winnipeg. Hours is good enough. So Gimli and Stonewall. And the next one on the list is Winkler. And the next one on the list is Morden. No, it's Morden. And Morden and Winkler, by the way, are literally right next to each other. They're essentially the same town separated by a little tiny stretch of road.
The Winkler people hate Ford.
Oh, they get along just fine. Gimli is 1.5. Stonewall is 0.5. So let's see. Let me make sure I'm reading these right. See, Winkler and Morden are basically the same. So 2 and 2. And Brandon is 3. But if we did this as an arrow diagram, we could simplify it a little. Let's mix them up. Let's put them alphabetical on the left-hand side here.
Well, that's fun.
So Brandon is first, and then Gimli would be second, and then Morden would be third, and then Stonewall, and then Winkler, W would be last. And okay, so Brandon, so let's put the numbers in numerical order too. 0.5, then the next biggest one is 1.5, then the next biggest one is 2, and then the next biggest one is 3. Okay, so Stonewall got to be the 0.5 one, so put an arrow to that. Gimli was the 1.5 one. Morden and Winkler were the 2s, and Brandon was the 3. So there we go. There's an arrow diagram. And one more example. What would this look like as ordered pairs? I'll just stick with the order that it was in the chart this time. So Gimli, comma 1.5. Stonewall, comma 0.5, only a half an hour away from the city. Winkler, 2 hours from the city. Morden, also 2 hours from the city. And Brandon is a 3-hour drive from Winnipeg. Okay, so that's basically it. You guys get some time to work today. So, oh, hold on. I thought I had my blog ready to show you. I do not. Here is what we've chosen now. A lot of these questions get really repetitive. You'll notice those two examples are even almost identical. So I'm not going to assign everything from this chapter. So read carefully what I've assigned. So I hope not to be wasting your time here. So let's see. I'm only going to assign, read this carefully, page 262, 3A. Don't bother doing 3B and 3C because they're basically the same question over and over again. So 3A and then 4, 7, 9, 13, 14. 13 and 14 actually are quite good as little spatial word puzzles. They're actually kind of challenging. The rest of this stuff is just like the notes. So 3A, 4, 7, 9, 13, 14. So you could probably finish that before the end of class. You've got a little over half an hour. No, more than that. You've got well over half an hour. So there you go. You've got time to finish that. Guys at home, let me print attendance here, and then if you'd rather just log out of the Wi-Fi. There you go. Okay, attendance is done. If you guys want to log out, you can. I'll leave the meeting open for 10, 15 minutes yet. If you get started and get stuck, you can come on back. Okay? Oh, Aurora, before you go, you're writing the test tomorrow at lunch, right? Does Aurora hear me? Or is she logged out already? I had originally said today at lunch. Aurora, I completely forgot that today is the same group that I saw on Thursday because Friday counted as a day. After I warned you guys about it, I totally forgot.
Right?
Oh.
Don't worry, I almost messed up.
Yeah.
My sister was like, "What are you doing up?" And I'm like, "I have school." Because normally she's
This
on
Friday does not count as bingo.
Next Friday
Oh,
will
it's
not count
next
as.
Friday, okay.
No,
Oh,
Good
okay.
Friday hits lands in spring break, so you don't really get a day off work.
Darn.
Okay, so you guys can get started on that. I'm going to, you know what I'm going to do? I'm going to get tomorrow's lesson ready. I don't think I have it on here yet, do I? Oh, I've still got the recording going.